Welcome to Technoverse. The dream of infinite clean energy is finally moving from fiction to reality. 2025 has triggered a massive leap in the race to build an artificial sun, and three nations just changed the game forever. Let's dive in. The immense energy that radiates from the sun, bathing Earth in light and warmth, is the product of a continuous and violent nuclear fusion process occurring at the star's core. Under extreme conditions, the nuclei of hydrogen isotopes fuse to form a heavier helium nucleus, releasing colossal amounts of energy. Driven by this understanding, engineers and researchers have sought to construct a miniature artificial sun on Earth within nuclear reactors. The goal is to harness this process for the production of inexhaustible, clean, and sustainable electricity. However, this endeavor faces immense physical and engineering challenges. In the sun, massive gravitational force compresses fuel to a density equivalent to 150 times that of water at a temperature of 15 million degrees Celsius. Since achieving this kind of gravitational pressure is impossible on Earth, scientists must rely on a different approach, raising the temperature to 100 million degrees Celsius. This extreme heat increases collision speeds far beyond those found in the sun, raising the probability of fusion to compensate for the lower density. At this superheat, atoms disintegrate, and matter transforms into a state of plasma, an electrically charged ionized gas. Here arises the greatest engineering challenge. How can plasma at this temperature be contained without melting the vessel that holds it? There is no known material in the universe, whether rock or metal, that can touch 100 million degrees without instantly vaporizing. To solve this dilemma, scientists turn to an engineering design known as the tokamak. This reactor relies on a toroidal or donut-shaped vacuum chamber surrounded by massive electromagnetic coils. These coils generate super-powerful magnetic fields. Since plasma consists of charged particles, these fields act as an invisible cage, forcing the hot plasma to float in the center of the circular chamber. This prevents it from touching the surrounding walls, protecting the reactor from melting while maintaining the stability of the reaction. The year 2025 witnessed a marked acceleration in the pace of testing, specifically in these experimental tokamak reactors. Three major experiments stood out this year in China, France, and South Korea, all seeking to solve a difficult equation: raising plasma temperature and keeping it confined for the longest possible duration. These two factors, temperature and time, are the fundamental prerequisites for initiating and sustaining a fusion reaction. It began in China via the East Reactor in Hefei. In January 2025, the Chinese Academy of Sciences announced an unprecedented achievement. The reactor successfully maintained plasma operation at 100 million degrees Celsius in a stable high confinement mode for over 1,066 seconds. That exceeds 17 minutes. This combination of immense heat and long duration served as a strong message to the world that fusion reactors are becoming capable of operating for extended periods without their systems collapsing, taking a giant step closer to commercial reality. Immediately following this, in February 2025, France announced a new global achievement via its West Reactor. The reactor succeeded in maintaining hot plasma at 50 million degrees Celsius for a record-breaking duration of 22 minutes. The strategic importance of this achievement lies in how it paves the way for the massive international ITER project currently under construction in southern France. The West Reactor serves as a critical testbed to verify the endurance of components and materials, specifically tungsten, over long durations, ensuring the future success of ITER's operation. Then came South Korea's turn in March 2025. Scientists announced that the K-STAR reactor successfully stabilized plasma temperature at 100 million degrees Celsius for over 50 seconds. Although the duration was shorter than its Chinese counterpart, the Korean experiment focused on plasma stability techniques and precise impurity control at this holy grail temperature, confirming the steady evolution of their magnetic confinement technologies. The results recorded in China, France, and South Korea reflect a significant evolution in plasma heating technologies to record temperatures and in improving confinement efficiency to maintain that heat for longer periods. It is worth noting that nuclear fusion experiments have not been limited to tokamak reactors. Experiments on other types and proposals for new designs do exist. However, the experiments of 2025 have demonstrated that tokamak technology is technically the most mature and the closest to commercial application. If you found this update valuable, leave a like and subscribe to Technoverse for more. We'll see you in the next video.